We can begin. Awesome. So the agenda for today is to go through some of the fundamentals of the functions and relations stuff. I know a lot of this is probably going to be pretty chill. There's probably only one major topic that people get wrong a decent amount of time, and that's with the maximal domain of different functions. So I'll more or less breeze through the other topics, and if you want me to dive into any more detail as to how those ones work, feel free to let me know. Otherwise, yeah, that's the overall pace. So, sets. Basically, a set is simply just a collection of items. These items are referred to as elements, and we use this kind of notation where some element called X, something called X is an element of the set A. So sets are usually given capital letters, whereas the individual elements of those sets are given as lowercase letters. If it's not an element, you simply take that exact same symbol and you do a strike between it. This says that some element X is in fact not an element of A. Sets are probably best described using Venn diagrams, one circumstance of which is a so-called subset, which simply means that one of your sets is entirely encapsulated by another set. So you can see the circle of B is entirely within the circle of A. The way you write that is you say that B is a subset of A using that particular notation. Intersection, that's just that spot on the graph. It's where they both overlap. And if you ever see this symbol, it simply basically can be referred to as just zero. There's just nothing there. Set difference is a little bit, you do see it a lot, but not necessarily in the context of this. You'll usually see it as like all real numbers excluding a certain value. So you usually see that with, I mean, I could probably pull up any of these really, and you might see it. Let's see, do we have an example? Yeah, there you go. Well, kind of. It gets used in domain sort of notation, where you have like a hyperbola, for instance. It'll have that sort of thing, where it'll say just like all real numbers excluding a certain value. But okay, that's that. There are different kinds of generic sets, one of which is the natural numbers, which are all the countable numbers from 0 up until infinity. Then you've got integers, which go both ways. Well, sorry to pull it back for a bit. Natural numbers is given by the double-stroked n. Integers is given by the double-stroked z. And yeah, integers just go backwards into negatives as well. Rational numbers, you'll very rarely see this, but if it does come up, it'll be given as the double-stroked q, and those are simply just your fractions. Anything that can be represented as a kind of fraction is considered a rational number. Irrational numbers don't necessarily have a letter that's dedicated to them. If you do need to describe it for whatever reason, you can say that it is all of the real numbers excluding the rationals. When you do that exclusion, all you're left with are the irrationals, where irrationals are things like pi, things like square root, e, all of these numbers that are like infinitely recurring, well, infinitely propagating decimals if it never ends, then those are considered irrational numbers. And then real numbers, this is what you're most familiar with. That's just everything in between positive and negative infinity. And so if you look at it all on a massive graph, you've got the natural numbers, which is encapsulated by the integers, which is then encapsulated by the rationals, which is then encapsulated by all possible real numbers. Anything in there worth going into any more detail on?
No, good.
All good? Okay. Next up, functions and relations. So basic function notation might look something like this. We kind of saw maybe a slight example of that, maybe as I was scrolling through it. The way it basically works is whatever's at the front here are the variables of the, well, this is technically all possible relations, but yeah, basically what variables are being used. So if you look at this rule here, it uses both y and x, and so at the front is going to be x and y. Those are your inputs and outputs. Next is the expression itself. That's just the rule of the equation. And then after that's going to be whatever the domain is, which in this case is going to be all real numbers. Domain and range. So domain, all possible inputs, usually all possible x values. Range, all possible y values, or all possible outputs of the function. Where things get a bit trickier is calculating implied or maximal domains, which simply just means all the possible x values that a function can have. I've since created a list of all the typical criteria for each individual function for what those maximal domains are going to be. So anything like linear, polynomial, exponential, those are going to have maximal domains of all real numbers. There isn't really anything you can plug into any of those types of functions that would cause it to break, mathematically speaking. However, when you get to logarithms, the key criteria there is that the brackets have to be positive. You can never have a natural log of 0, and you can never have a natural log of a negative number. So that's the criteria you need to be worried about there. Sine and cos, all real numbers, there's no real issues there. Those propagate out to infinity no matter what. Tan, kind of, but you just got to make sure you exclude all those asymptotes. So basically anywhere that there are vertical asymptotes on a graph is always going to be an undefined spot. Hence, it should not be part of the domain. So you would have to calculate asymptotes and exclude that if you're doing maximal domain for tan. Hyperbola truncus, exact same thing. You want to exclude those asymptotes. To be more specific to the hyperbola or the truncus, you just want to get rid of that divide by 0 possibility. So you have your 1 over x or you have your 1 over x squared. Whatever would cause that denominator to go to 0, you want to get rid of that possibility. For any even root graph, so we're talking like the square root, the fourth root, the sixth root, all of that, the inside of the root has to be greater than or equal to 0. So you can never have a negative inside an even root function. Square roots can't have negatives, fourth roots can't have negatives, none of that. Although strangely enough, the odd roots, so like the third root, the fifth root, the so on and so forth, all those odd numbers, they actually don't have any restrictions. They can go negative. And you might remember that from the cube root just being like 3 numbers that multiply together to give a number. And when you have 3 numbers, you can actually ping pong between being negative and positive. So that allows you to have all the numbers as part of that. That's just an overview. I do have examples of all the ones that you need to actually solve, starting with the logarithm. So if you remember, the criteria for a logarithm is simply just that you want the brackets to be positive. That's it. So you take whatever's inside here and you make it greater than 0. All you do from there, rearrange, and then that gives you your solution. It might not be as simple as just rearranging. If this is like a quadratic or anything more complicated than that, then you might have to use some other techniques to figure out how to actually solve that particular inequality. But largely speaking, you're probably going to get a linear most times. For tan, the idea is you want to get rid of those asymptotes. And so first things first, we got to find those asymptotes. My preferred approach has always been to convert tan into its sine divided by cos equivalent, and then figure out where cos goes to 0. So we're just going to rip that cos out on its own and figure out where it goes to 0. That's going to occur at plus minus pi over 2. And then because we're doing all possible x values, we're going to do its general solution. We're going to add that 2 pi n to it. Then from there, just rearrange that left-hand side. That's going to give you either 2 pi n or pi plus 2 pi n, which we then realize if you think about it a little bit, both of those solutions can actually condense down to just pi n. So for instance, if you consider n is 0, then that gives you the same thing that this would give you, 0. If n was 1, then you get pi n, you get pi for that. That's the same thing as if you had done negative, wait, which one would it be? If you have n is 1, you get pi. Where is it? What would give you that? Not negative. This would have to be... Oh, does that actually not work? Uh-oh. Hang on a minute. Let me double check that on the CAS. I check for where cosine equals 0, and I give no domain. Many 1 cosine x minus pi over 2 equals 0, comma x. Okay, it is just pi n. I guess I'm just losing it a little bit to figure out how we get pi out of that for the for what I've got here. Anyway, no worries. Point being, it does end up being pi n. That gives you your general solution for all asymptotes, and so all you do is you say, yep, x can be all real numbers excluding pi n specifically. It's probably worth pointing out that you want to put the qualifier on that n has to be a natural number. Otherwise, you're slightly inaccurate in your answer. Next up, hyperbola. So hyperbola, you just want to make sure any divide by 0 errors. Again, get rid of those. In this case, the denominator is x plus 3. And so all we want to do is figure out where does x plus 3 equal 0, and then be sure to exclude that from the domain. Exact same thing with truncus. There's your denominator, make it equal 0, and then get rid of that as one of the possibilities. For any even root, so this is just the square root, you want to make sure this is greater than or equal to 0. So the thing that people tend to get backwards is between the logarithm and the root. Logarithm can't have 0, root can have 0. And so that's why we put a greater than or equal to sign on this one, and then rearrange that. The last, or at least I believe, is this the last? Yeah. The last example we'll have a look at is what happens when you actually have a combination of functions. So there's no like generic understanding of what this graph would look like. And so the overall approach is to break it down into parts. So I guess before we try this one, was there anything from the previous examples that's needed to elaborate on?
No, I think it's all good.
Okay. So from here, there's a couple of parts. First thing you want to do is identify what are all the components to this function. We've got a square root, so we've got an even root. We've got a natural log, and the other one's a bit tougher to maybe see for the first time, but we've actually got a division, right? Division is also one of the things we're looking at. So once you identified each of those components on its own, we now just want to consider what each of those components has a maximal domain for. So for a square root, we know the brackets have to be greater than, or the inside of the root has to be greater than or equal to 0. So you take that x plus 2, you get your solution. That's one little part. Next up, you got a logarithm. Logarithm has to be greater than 0. So again, we're going to chuck that as greater than 0 and solve that part. As I said, division has made an appearance, and so what you want to do is make sure that you've gotten rid of any possibility of your denominators being 0. So you take the entire denominator there, natural log of x minus 1, and you see what would it take to make it 0, and we're going to make sure we get rid of that. In this case, it's a matter of rearranging to become an exponential. So same base, whatever's on this side comes in as the power, whatever's in the brackets of the logarithm comes out front. E to the power of 0 is just 1, and so when you add 1 to both sides, you're just going to get x equals 2. So this is a good domain. You want to have all of that to make sure this is good. This is also a good domain. You want to make sure all of that is good for the logarithm. This one's what you don't want to have happen. So when you're doing your own working out, it might pay off to put like a do not equal sign on this. In fact, yeah, I'll make myself a note to update the resource to say do not equal. Do not equal example 6. That way you don't get confused when you're doing your own handwriting. So we've got all these possibilities. We need to make sure that all of them are true at the same time. Because if any one of these things breaks, then the whole function breaks. So we're just going to do our number line. The easiest way to go about this is to do the two inequalities first. That way you can see what the major overlap is. And so if you do the two inequalities, we had greater than or equal to -2 for the root. We had greater than 1 for the logarithm. That's that. And so the intersection is going to be the same as the greater than 1, at least for those two things. From there, we're just going to make sure we get rid of that x equals 2 possibility. So we want to cut off that little spot there. And so basically, we can do it in two separate parts. You can say it's the full interval from 1 to infinity, not inclusive of the 1, of course. And then you're just going to make sure you exclude the 2. TI Inspire users actually can just flat out use the domain function. You literally just type out the function, comma x, and that will give you this specific notation here. I don't know if there's a nice navigation for it. Like there's no like menu to be done. I believe you just got to go in the book icon. So there's this book icon here. And if you just click the letter D, it'll take you to all the D functions. And then from there, just scroll all the way down until you see the word domain, which is that. And then you put in whatever function you want to put in there. So if I put in the full thing that we had, square root x plus 2 over natural log x take 1, comma x. That gives you x does not equal 2, and x is between 1 and infinity. So all you got to do is reword that a little bit better to be in the actual set notation when you put it down as an answer. That's by far as tough as those are going to get. So anything worth clarifying there?
All good.
Awesome. Okay. The rest is just going to be a bit more of terminology. So first things first, what is a function? Well, it's a specific kind of relation that passes the vertical line test. So basically, I've got this quadratic here. I can draw a vertical line on this graph anywhere I want, and if it only intersects once, which it does, then it would be considered a function. So basically put, you don't want to have anything that goes back on itself. So if I draw a random relation, typically the graph of y squared equals x, this would be considered a relation because you can draw a vertical line and cut twice. As far as function notation goes, the notation is as follows. So basically, you give the name of the function at the very beginning. So if we look like down here at one of the examples, this function is called f of x, and so the first letter at the front is going to be f. Next thing after that is the domain. So that tells us that the domain of this quadratic is going to be all real numbers. The next thing after that is the codomain. We don't need to worry about what that is. It's pretty much always going to be all real numbers. It pretty much just tells you what set of numbers does your domain map to, basically speaking. Probably a bit more nuanced than that. Point being, we don't really need to know the nuance behind it. And the last thing is obviously just going to be the rule of the function. It's a quadratic. And so if we look at another example, this would be a hyperbola that's defined from -5 to 5, excluding 0. That's more or less all you need to be able to understand. One-to-one functions, those are a special kind of function that also passes the horizontal line test as well. So our quadratic from earlier was good at passing the vertical line test, but not so good at passing horizontal line test. So basically speaking, when you have a one-to-one function, it just means that the function can never, how would you say, It has to be either always increasing or always decreasing. So if I were to draw some non-typical examples of one-to-one functions, I might draw something like this, which just sort of waves up and up and up. It's always increasing, but even though there's bends in it, no matter where I draw a horizontal or vertical line, it'll still only touch it once. And for that reason, this non-typical function would still be considered a one-to-one. That's obviously not particularly likely to have happen. Um, Other one-to-one functions include stuff like exponentials, stuff like logarithms. Um, that shouldn't have gone back on itself. Logarithms don't go back. What else? What else is one-to-one? Yeah, I mean, point being, you'll be able to tell by doing the horizontal line test. Um, Worth pointing out, you need to pass both tests. So, like, this thing here would not be considered a one-to-one function just because it passes the horizontal line test. It needs to pass both the vertical and the horizontal line test. And I believe last in this document is on piecewise functions. So piecewise simply just means, hey, here's a set of graphs, put them all on the same axes. That's really all it boils down to. The notation is basically just rule 1 and domain for that rule. Rule 2, domain for that rule. So if you look at the piecewise function described in screen share, you've got y equals 0 for all x less than 0. That's going to be this little section in here. Then you've got the graph of 2x plus 1, and it's going to be from 0 to 1. That's that section. And then lastly, minus x plus 4 for everything greater than 1. That's going to be that whole section there. And that's it. Anything to clarify further?
All good.
Easy. Okay, so the only thing probably worth touching on would be maximal domain questions. So I'm curious to see if there's any in here that look like they'd be tough. We'll start with some of the fundamentals there. What I'll do is I'll grab a go at my cheat sheet. Yeah, I'll put this in the chat so you can refer to it should you need to. But otherwise, yeah, we'll just smash out some maximal domain questions. Probably also worth pointing out, since you're the only one here, we can do another thing if you want to do another thing. But otherwise, this is the agenda. Okay, so question 8. Okay, I'll probably do some quick fire ones depending on how confident you are with the questions. So we'll go question 8. At least start with A here. Yeah, let me know how we go. Oh, we'll just say stating maximal domain. We won't do the sketching side of things.
Would it be 5/2?
5/2 is a good number to have, but that's not the answer necessarily. How do you format that into an answer? You've mathematically found the correct thing, but now you just got to format it a bit.
Would it be negative infinity, comma 5 over 2 union 5 and 2, comma, infinity.
Yep. Yeah, that sounds good. What brackets did you use for the 5 on 2? Rounded or square?
I used rounded.
Yeah, and rounded is correct. Nice. Yeah, totally one way of doing it. That's using the interval and union. Otherwise, you've also got the possibility of saying all real numbers excluding 5 on 2, and you can use those squiggle brackets. That's a nice, well, it's a shorter shorthand of doing that, but both is perfectly accurate. Yeah. Um, we'll do one of the square roots, so let's just say b. Actually, b is basically a cut and copy. We'll do c.
I got negative infinity to 5 on 2, square bracket.
Yep, 5 on 2 square bracket. That's good. Nice. Bit of a pro tip, I guess. If you ever found doing the sketch for these weird, when you've got like a negative on the x and it's sort of rearranged, I know that can throw people. One thing that can kind of help with that is just do the maximal domain. Because if your maximal domain says it shoots off to negative infinity, you know the square root's pointing left instead of right. And so it can be a nice sort of way of just like recalibrating your brain and being like, okay, yeah, that's how I sketch that. Um, otherwise, yeah, most of these are going to be pretty chill. You can either, yeah, explain to me maybe how you'd go about E. You can either just solve E, or you can just let me know what has to be done differently. We're the only one that's got a bit of a trick to it.
Could we just make it in a square root? Like put it in a square root?
Yeah, yeah, it is just square root. Yeah, power of half, same thing as square root, so exactly the same as what you just did there. This one, that you don't really need to know how to do. That's when we start looking at relations, which isn't super accessible. A lot of, well, it never appears on an exam, and a lot of schools don't do that. Does your school, has your school covered any of this before? Because if they do, we can do it.
Like F?
F, yeah.
No.
No? Okay. Easy enough. We can skip that. Cool. So those are the fundamental ones there. I did go through some of the SAC/exam questions and try to pull out which ones are interesting and worth doing for that. So really it's going to be this part B here, which is figure out where f of g of x is defined. So I guess I'll just quickly ask, do you remember what f of g of x means?
Is it the composite function and like fog and stuff?
Yeah, exactly. Composite function, specifically fog, correct. So you're going to need to do a bit of background to get up to part B. So have a read of how question 4 is going. First, let me know your answer to part A, then we can move on to B.
I got x plus 8 and x plus 2.
Yep, that is correct for the inside of the brackets. Um, that's good for the purposes of what we need it for. However, one thing I do want to highlight just for the fun of it is the question has asked you to find integers c and d. And so if you write your final answer as what you just said, technically not answering the question. So how would you rewrite that a little bit to fully answer the question here?
Would I say C is 8 or something like that?
Yeah, something like
D.
that.
Yeah.
Yeah. Now, the weird trick here is that technically C and D have two possible solutions each. You either have C is 2 and D is 8, or you have C is 8 and D is 2. That could be in
Yeah.
either thing. And that actually matters. Like, I'm looking at the exam report now. This was a VCAR exam, and they said this or that. And so it's worth pointing that out when you're doing these kinds of questions. You want to make sure you don't mess up those pairs. But that's more of a exam tip rather than this lesson tip. And then, yeah, now that we have that, now we want to state the maximal domain for that composite function. A bit trickier here.
I'm not sure.
Not sure. Okay. Um, you probably have some idea of what to do. So, any thoughts on what you might do to start working towards it?
Um, would we make it greater than or equal to 0?
Yeah, greater than or equal to 0. Absolutely. Great start. So, that's probably where you had your blocker, which was how do I solve that? Is that fair to say?
Yeah.
Yeah. So, we have our x plus 2, we have our x plus 8 greater than or equal to 0. Doing the algebra on this, technically doable. You would have to do something called sign analysis on it, which basically means the only way that these two terms will be greater than or equal to 0 is if you have a plus and plus, or you have a minus and a minus. And so one of the ways you can do it algebraically is figure out where is this plus, where is this minus, where is this plus, where is this minus, and then do the intersections of those two things. Doable, but slow. Much better is to get a visual going. If I were to tell you to sketch this, what would you do to sketch it? Just sketching that quadratic.
I've forgotten.
Forgotten? That's fine. So this is a null factor law situation. When you have a set of bracketed terms that are multiplying together for a polynomial, you basically make it so that anytime these brackets equal 0, those are the x-intercepts of that function. So x plus 2 means you've got to cut at minus 2, and x plus 8 means you've got to cut at minus 8. That gives you x-intercepts to start with. Then, overall speaking, you've got to determine, is this a positive or a negative parabola? What is it?
Positive?
Positive, yeah. If you expand this all the way out, it's going to have a positive x squared term, and so it's going to point upwards. It's going to do something like that. Now, the reason why any of this matters is because what I've just sketched is this. And so if I want to know where this is greater than or equal to 0, it just means where are my y values greater than or equal to 0. That's going to be all of this over here and all of this over here. And so basically it means as long as my x is greater than -2 or less than -8, I'm good. I'm above or equal to 0. I meant inclusive on these, but yeah. So the preferred way of doing any inequality where you have a polynomial, or basically any function that you can sketch, is to sketch it. Like this could have been a logarithm, where is natural log greater than or equal to 0? That could also be potentially a tough question. So you would just sketch your logarithm and then look, where is it above or equal to 0? And so putting it all together means you can write this in two separate ways. Your preferred approach is probably to say x is an element of -infinity to -8 inclusive, union -2 to infinity. That seems to be what your notation that you like using. The other alternative, just so you've got options, is you can say or start with all real numbers and then get rid of the section that is not included. So you don't want the -8 and you don't want the -2, the non-inclusive of those. Either of those is up to you there. Fair enough on how that works?
Yep.
Sweet. Because you're going to do it again in another question, which is, yeah, part B of question 2. Exact same idea.
I got negative infinity to -1 union 3 to infinity.
That seems good. What brackets?
I did rounded ones.
All rounded. Yeah, good. Crushed it. Yeah, nice. Okay, that is that one. And then I think the last and probably most complicated of these would be this part here. So requires a little bit of background. So yeah, 10 minutes we can do that. We'll spend a bit of time on actually grabbing the rule of this function here because it will be required for solving this. Yeah. Might be a bit tough for you if remembering how to handle the bracketed terms was a challenge. I'll give you a couple of minutes or so. Sing out if it's a bit tough.
I'm not too sure.
Not too sure. Okay. So the hint or kind of hint that I had earlier was that it requires understanding how to do like those bracketed polynomials. So the first thing of note is that all x-intercepts occur as like a bracketed term. So kind of like how, if you look back at maybe the handwritten bit, we had like our x plus 2, x plus 8, and those corresponded to -2 and -8 on the x-intercepts. It's the same thing here, where our polynomial cuts through plus and minus x equals 1. And so that means that when we do our bracketed terms, or at least part of them, we're going to have x plus 1 and x minus 1, definitely as part of it. Fair enough so far?
Yep.
Okay. Next up is another x-intercept that is on the graph. It's at the origin specifically, but it is a turning point, and we handle that a bit differently. Any thoughts on how we handle that ever so slightly differently?
Not really.
That's okay. So it just means that if it's a turning point on the x-axis, rather than cutting straight through, you square that term. So because it cuts at 0, that's the same thing as saying like x minus 0, or obviously just x at that point. But because it is a turning point, we now square it. And so this one's going to have a leading coefficient of x squared. that tells you turning point at x equals 0, cuts at x equals -1 and +1. That's almost everything. The last thing to consider is anytime you do these families of functions style things, there's always a coefficient of a at the front. And so you have to figure out what that coefficient of a is, usually by subbing in a known point. And one of those known points is 1 over root 2, comma 1. So if you let y equals 1 and x equals 1 on root 2, well, you're going to end up with just subbing in exactly that. 1 over root 2 plus 1, and then 1 over root 2 minus 1. So you'd have to expand all of that out. That has work solutions to it, so I won't really touch that too much. That does end up giving you a equals -4. This is more so just the fundamentals to get to the next thing, which is having this rule is, or at least nice to know. But yeah, all we're doing is expanding that out to get the a equals -4. Now, where this is related to what we've been doing is now it's like, okay, this function g is trapped inside the logarithm. We're told that g is the same as f. So this graph that we have up here is what's trapped inside this logarithm here. Our goal is to figure out the maximal domain of both sections. So you've got this natural log of this whole thing, and you've got this natural log of, well, all of these. So to make sure you have, well, to find the maximal domain of this, what things would you maybe consider?
Sorry, what was the question?
To find the maximal, say that again. To find the maximal domain of this, what would you start considering?
You would make it greater than 0.
Yeah, yeah. Making what greater than 0 though?
The x cubed plus x squared.
Yep, that's one of them, absolutely. So we're going to have x cubed plus x squared greater than 0. How do we now solve that?
We can expand the x cubed and make it x squared and then bracket x plus 1.
Oh, yes, yep. So x squared bracket x plus 1. That's good. Nice.
And then you're left with x squared is greater than 0 and x plus 1 is greater than 0.
Yes, that's sort of what I was talking about here, where you can do your little like plus plus and minus minus, and you can
Yeah.
figure out how that works. As I said, there is a fair bit of work to be done there if you want to take that route, but it's doable. I feel like you're going to say something.
No.
No, okay. So instead, better off is sketching. So once you're used to sketching, you'll realize that x squared just means turning point at the origin. X plus 1 means a cut at -1. This is overall a positive cubic, so it's going to start bottom left, end top right. So if it starts bottom left, it's going to come through here, it's going to turn there, and then end at top right. So this is polynomials revision. If this is a bit like rusty for you, then just check out the classroom tab of functions, relations, polynomials. It'll go through how to handle all this stuff. And so yeah, if you want to look at where this is greater than 0, well, it's going to be from x equals 0 onwards and between -1 and 0, both non-inclusives. So that gets you the first logarithm term sorted. We've sorted out the natural log x cubed plus x squared. That's this thing. But that's not all we have. We've also got the natural log of g of x, which was, if I quickly redraw what that looks like, was this sort of thing. So if we want this to also be maximally, well, if we want this to have a maximal domain, what do we do here? should probably put the actual ticks on these. That's -1, that's 0, that's 1. How do we maximally define this one?
Would it be x plus 1 like bracket and then x minus 1 bracket is greater than 0?
Yeah. So if you want to do like the function thing, you could grab this that we created earlier. That was like the whole polynomial, and you can make that a greater than 0 situation. But the whole point of that is to then sketch it. And so since we already have the sketch, we can just sort of say, yep, we want this to be greater than 0, which means everything from here to here and everything from here to here. So I guess I was kind of wrong in that we don't really need the rule. You can just use the graph of it. But yeah, so that means you've got this section. Now, because of your time, do you want to have a think about how to combine them, or shall I just talk from here?
You can.
Yeah, sure. So basically, because our function is the subtraction of these two logarithms, you want to make sure both are defined at the same time. So you want to take the solution from here and intersect it with the solution from here. So number line speaking, this one's good for everything to the right-hand side, where this one got to cut at 1. And so the intersection of those is going to be from 0 to 1 on this right-hand side. And then over here, these two already match. This is -1 to 0, this is -1 to 0. So we're going to have -1 to 0. Still going to chuck a union between them because you want both of these things to be true to maximally define it. That, I believe that's everything. Did I miss anything there? No, that's fine. Cool. So that's how you do that one. Anything to clarify further there?
No.
Easy. All right. Well, that's about it from me then. I'll leave you to it.
Thank you.
No worries. Have a good one.
You too.